So, hi everyone. I'm Maxim, and I like dependently typed programming languages. So that's why I've been thinking about dependently typed choreographies and how one would go about making such a thing. And well, I found a way, and I started building it. It's going to be Kami. It's very early, but I want to tell you about how well, yeah, how I did it, and the thing which allowed me to do it, because dependent types are very complicated, and I found MTT, which is Modal Type Theory by Daniel Grazza from last year, which is his PhD thesis, and it's a type theory with dependent types and which allows for arbitrary modalities. And I found a way to use his general framework to find an instantiation of it to reproduce choreographic programming. And this way you get the dependent types for free, kind of. Well, and the journey started with the functional choreographic programming paper, which Fabrizio already introduced, which is the Chorλ programming language, which is a functional choreographic programming language. And this gave me the idea to think further to the dependent types. And, well, how do we do this? There are kind of, like when you think about it, there are two worlds, two modes in choreographic programming. We have the code, which is running locally. It's like we have natural numbers, we have sum types, we have function types, products, whatever. And we have the global world, which is the different locations and nodes and processes. It's like we may have natural numbers located at some node U. We may have some globally distributed knowledge of choice. And of course, we have function types, which are our choreographies. And I take this distinction of two worlds very seriously. So the types of Kami are defined as follows. We have two versions of types. Oh, well, yeah, let me tell you. I write triangle for the local mode and circle for the global mode. The triangle is like a piece of cake, and the circle is like the whole cake. So we have our local types, which are whatever types we want to have, like functions, products, and so on. We, like in the full MTT, there are also dependent types there, but I skipped them for the talk. And we have the global types, again, all types. And now, so the point is, all the standard types have perfectly standard terms and typing judgments. They're exactly the same. The only the magic comes in these two new type constructors. One is the add type constructor you might have seen from choreographic programming, where we have a local type at some location. And I also introduce a new type constructor, which takes a global type and puts it locally. So the meaning is we can have, when we have a choreography, we can represent it locally. Like the projection to each location, we take them simply as a tuple and have it locally at the location. So yeah, exactly. So the meaning of the add constructor is, of course, like when we simply project it into a set. If we have a location U and project it to location V, of course, it's the interpretation of A if they are same and the unit type otherwise. And on the rest of the type constructors recursively. And now the interpretation of my new box constructor is a tuple of all the local projections of the global choreography type X, and recursively on all the rest. Now, how can we work with these modalities? So first, the idea is when we want to construct something under an at u modality or under the new box modality, then we can only use variables in the context which are under the same modality. This means that, for example, we want to construct a tuple, like a global tuple where A is under U and B is under U. Of course, we can use such a tuple at the U location. And we can also have the same, like the reverse function. And just as well, if we have a local function located at U, we can turn it into a choreography mapping A at U to B at U. And the same thing works with my new box modality. Now, this is the default behavior of modalities in MTT. And without adding further things, we of course cannot build a function which creates A at V from a value A at U, right? Because we cannot, this should involve communication, and we haven't added communication yet. And also, box of A at U is a local value. It's like the choreography where the choreographic type, let's say, where A is at U as a locally defined choreography. And this is simply the type A. Also removing modalities randomly is also not allowed in, without adding further primitives. Okay, so this is how the basic modalities work in MTT. Now we want to add actually the communication primitives, right? So for that, I want to introduce some notation. I told you the at modality takes local types and turns them into global types. Now I want to allow to compose modalities. So we can take box at U, goes from global to global. We can take even three, at U, box, at V, local to global. And I also allow the identity modalities which don't change the type. So now if I have an arbitrary modality which goes from one mode to another, and I have a type at this mode M, then I write these angle brackets for applying this modality to this type, right? So for example, if I have natural numbers and apply this triple modality, then I'll get an at U boxed at V. Okay, so now let me introduce the communication, the two primitives with which we can actually write choreographies where things interact. And the first one is actually one without any communication. It just, I introduce this new primitive where I say if I have a local value of type A, then I can put it into a locally choreography where this type is at any location. I might, it's like scheduling. I might schedule it to U, to V, to W, wherever, but it's not there yet. It's just in the type tracked where I want it to be. And then here's the main thing. I have broadcast. If I have a global choreography type X and I have it boxed at a location U, then I can turn it into the actual choreography type X. And so this primitive involves sending the projections to each participant involved in that choreography. Yes, and now I have to tell you that actually I don't add only these primitives, but I allow them to be under any modality mu, right? So before we had A to this thing. So now actually I say that, okay, under mu and here again under mu. And this whole thing under nu and here again under nu, because I need to be more flexible and do things under modalities. Right, that's it. That's kind of how I recreated choreographies in MTT. So now let's see an example. We can reproduce the communication primitive from Chorλ by, the type is, of course, we want to send something from U to V. And how we do it? Well, given such an A at U, we first prepare, schedule the A to be located at V. So we have this triple type And then we simply broadcast, like we actually broadcast this, this choreography to, well, in this case, only V. And we have our function. Now, of course, this thing is, it's not only communication, right? It's a little bit more powerful. And in fact, this can reproduce the, like, the problem of Chorλ was that we need to somehow take into account knowledge of choice, right? When one process decides to do something, other involved processes need to know about, like, what choice it was. And we can reproduce that without any partial projection functions, but it's just already available built in the sense that we have both a local sum type and a global sum type. Like, if I project this sum type to all components, this means, okay, well, the node U has knowledge of A or B, and all other nodes know nothing. But when I project this sum type, this means, well, the sum is global, means all have knowledge of, like, every process have knowledge of the choice. But the actual data is, of course, only located at the node U. So the point of, like, communicating choice is just a matter of turning such a sum type, like, into such a sum type, which means I tell the other processes which choice I want to make. But I don't necessarily communicate the information which I only locally want to continue with. So, like, to write a function, is very easy, but I skip because it's a little bit long in the pure MTT syntax. So the point is that we first construct a function which takes our local type into a boxed at U thing, and then we simply do a broadcast after that. And yes, I call this whole thing globalize. Well, so the thing is, we can do the same thing with other data types. If we have a list which is only locally known at U, we can, in the same way, globalize it to have a global list where all participants know, know the length of the list in a sense, but don't have the data. And again, when I do a global pattern matching on this list, all participants know which branch we take, but only my U has the actual data. So in this way, there was an example in Chorλ where there is a function, an f, only available remotely at node V. And we have some data at U, and we want to use this function at V to map it on this list. So in MTT with my instantiation, this would look like, first, we can globalize the list to be able to, like, globally choreographically pattern match on it. And then we can simply do, well, recurse that's kind of the logical thing, right? When we have we can recurse on the list, communicate each element individually to V, and use f there, and call our map recursively, right? Okay. So now this has been one instance of modal type theory, and the thing is that, like, generally modal type theory is parametrized. We have, like, the definition starts with, well, let's see what a mode theory is. And for every mode theory, you get one instance of MTT. And the mode theory is, well, it's first a set of modes. In our case, it's only local and global, right? Then we say, for every pair of modes, we decide on the set of modalities between them. In our case, these are the add and the box modality. And then we say, well, between modalities, we allow transformations. In my case, these have been the prepare and broadcast transformations, right? So now with this thing, it's very easy to extend what I have told you, to extend with new features. For example, well, yeah, this is how my MTT looks. Right, the modes are the local and global. Here are my modalities, and prepare and broadcast are my transformations. Now, for example, let's add a new feature, which is common knowledge, common locations. For example, we might have a data type located at 2 nodes, and both nodes know its value. So very easy in MTT. What we do is we say, well, our add modality now takes subsets. And we add a new transformation, which says that if we have a subset V of U, then we can narrow the globally known A to one subset of the participants. Very easy. You just put in the new mode theory, you get a new full type theory, right? Or, for example, until now, my global world always involved all processes. Even those nodes which don't participate in the choreography, will have to communicate, will have to receive the knowledge of choice, right? We can do a little better, and we can say, well, actually, we have global modes for every subset of locations. And then we say, okay, we can include, of course, a choreography involving U, where U is a subset of V, is also a choreography involving V, right? And then we have a more fine control over which nodes actually communicate, and we can control this behavior. So in conclusion, choreographies fit kind of extremely well into this framework of MTT, and it's very easily extensible, and we get dependent types for free. The downsides are that the endpoint projection is a little bit more complicated because the types allow for more freedom, and this is kind of what I'm working on, still work in progress. So yeah, that's it from me.
Thank you for your presentation. We are open to questions.
Hi, thank you. This was a really interesting talk. I'm a little bit curious about how I should interpret something like A at U boxed at V.
Yes.
Can you give me a bit of intuition about how to interpret that?
Yes, sure. So where did we have it? Here, right? So first the outer modality says that this whole thing is located at U, only at U. Now the box says that now we want to have a choreography, right? We want to have a whole choreography, but this whole choreography is actually only a single value A, which should be located at V. It's like into the box, you could put a function type, right? You could put a function type which maps things from many locations to each other, whatever, right? But the only thing we put inside is this value A located at V. It's like at U, schedule the choreography where A is at V. Oh, wait. Sorry.
Thank you for the really nice talk.
Yes.
Could you go to the slide where you had globalized list?
Yes. I guess that's...
So this, this got me curious. Also, your previous slides about how to represent knowledge of choice, because in Chorλ we have these distributed choice types. I mean, I'm quite sure you could write a globalized list in Chorλ, right?
I think you don't have because you only allow for the adds at specific locations.
Yeah, but you can write a pair where the different components are at different locations, and then you can write a list of tuples with different types at different locations. And we use this in the follow-up EQ paper to show that you can model distributed knowledge about the choice. You just mention it, right?
Mm-hmm.
So I was just wondering if you had any thoughts about what are the real expressivity differences between programming like this and programming by using fine-grained knowledge choice, where you communicate this knowledge through selections and stuff like that. Did you look into it, perhaps?
The thing is, the fine-grained control, like from my point of view, I don't see where it's necessary. Because usually when you want to program like like from a normal functional programming point of view, you already have in your mind the different sum types you want to pattern match on. And the goal is only to like get the information to those nodes which need it. So like from this point of view, the fine-grained control is kind of not necessary in the sense of you can reproduce all those select statements again with this thing, right?
Thank you very much again for your talk.